Our universe, as we have noted on a number of previous equations, is partitioned in a particular kind of way. Well, first of all, actually, we can set aside one aspect of our universe, namely space and time. They sort of play a role of a stage, and prior to string theory, space and time really were separate things from the forces and the matter that exist in the universe. String theory, in fact, gives us a different viewpoint where space and time is actually part of everything else and vice versa. So we're going to concentrate on the other stuff, namely the parts of the universe that lead to creatures like us. Well, there are two things that we can speak on in that regard. There's matter. We've been through a long list of the objects that make up matter. They're the quarks, up, down, charm, strange, top, and beautiful. And then there are the leptons, the electron, the muon, the tau particle, and their associated neutrinos. So that's matter. And then there's the other part that's important for constructing beings like us. Namely, you have to take these fundamental building blocks and hold them in fixed patterns in order to get our parts. So the forces are 4 in number. There's the gravitational force. It's the weakest, but in some ways the most important because the large-scale structure of the universe is governed by gravity. There is the weak nuclear force. The weak nuclear force, the simplest way to think about it is that if you take a neutron and separate it from the nucleus of an atom, on average, after 1,013 seconds, the neutron gets replaced by a proton, an electron, and a neutrino. Now, the neutron that you began with was neutral. The proton that you have afterwards is positively charged. The electron afterwards is negatively charged. And so you had to have those two occur, otherwise you would not conserve charge in this process. And then there's this other relative to the electron, the neutrino, that also comes out of this decay. This process is called beta decay, and the form of energy that's responsible for beta decay is the weak nuclear force. There's electromagnetism. We're, of course, all familiar with electromagnetism. That's what our high technology utilizes in order to raise standards of living and basically create a way to go about life that was unimaginable, perhaps at the beginning of the last century. And then finally, the strong nuclear force. So we have matter and the forces that act upon them. Now, if we restrict ourselves to only matter, and I'll call the forces energy, I'll use the words interchangeably, there's something else that's rather obvious. All of the matter objects have the same spin rate as the electron. They can spin counterclockwise at a rate of 1/2 h bar, or they can spin clockwise at the rate of 1/2 h bar. The force carriers, on the other hand, have spin rates that are very different. The graviton spins at 4 times the rate of the electron. The photon, the intermediate vector bosons, and the gluons all spin at twice the rate of the electron. And the Higgs particle, which we haven't said very much about, but plays an important role that we will come to, actually doesn't spin at all. It's a spinless object. Now, the reason I point out spin is because that tells us what obeys the laws of chemistry and what doesn't. Electrons gather around atoms in shell structures. This shell structure is governed by spin. If you imagine, for example, gathering quarks in some kind of a structure, it would have to look very much like an atom because the quarks have the same spin. On the other hand, if you imagine looking at, and we can imagine because we can do it with mathematics, you can imagine trying to build an atom with photons, the shell structure disappears because anything that spins at 2 or a multiple of 2 times the rate of the electron does not obey the Pauli exclusion principle. There's a problem that we can perhaps think about. Why is it that all of the forces do not obey the Pauli exclusion principle and can never lead to a shell-like structure, whereas all of the matter fields do obey the Pauli exclusion principle and would always lead to something like a shell structure for atoms? After all, would not our universe be more balanced if some of the force carriers obeyed the Pauli exclusion principle and others did not, while other of the matter particles would be some obeying the Pauli exclusion principle and others not? Wouldn't that, after all, be more balanced? Well, the answer is intuitively yes. So let's go back and look a bit at our universe and its building blocks as we assemble them. There are the quarks, the leptons, up, down, charmed, strange, top, and beautiful, and we'll assemble together the force carriers. All the force carriers are in green. We have the quarks and the leptons in either red or blue. That's what our universe looks like. This is the modern version of the table of elements for how to build a universe in your basement. Now, in our discussion of the string, we came across this very peculiar property called supersymmetry. And we needed supersymmetry in order to banish the tachyon from the mathematical structure of the string. In order to have supersymmetry for every bosonic strand of the string, there had to be a corresponding fermionic strand of the string. If you want an analogy, in order to banish the tachyon, it's kind of like having people coming to a bar. If they come in pairs, then the bouncer will let them in. But if they come singly, the bouncer tells them they can't come. That's kind of how supersymmetry works. It says things must come in pairs, where one member of the pair is a boson, or a boy, and the other member of the pair is a fermion, a female. So, is our world supersymmetric? Well, that's something we can do simply by counting, because if supersymmetry is around, there should be equal numbers. So let's do some counting of the standard model. Well, we have 18 quarks. Remember, they come in 6 flavors times 3 colors. We have 6 leptons, and so that yields a total of 24 fermions in our universe. Now, we can't actually use the number 24 because that's not actually correct in the counting. We have to be a little bit more careful. Remember, the electron actually comes in 2 varieties, spin up and spin down. So instead of counting the electron as one object, we should at least include the effects of spin. The other thing about the electron that we must take into account is that it has an antiparticle. So in fact, an electron really counts for 4 different objects: spin up, spin down, particle, and antiparticle, and then spin up and spin down for the particle and antiparticle. So that's 4 objects. So really we must take this 24 and multiply by 4 in order to count what we physicists call the fermionic degrees of freedom in our universe. And the answer turns out to be 96. So we have 96 fermions in the universe. On the other hand, we can count the force-carrying particles. There are 8 gluons, 1 photon, 3 intermediate vector bosons, and the Higgs particle. So we can count those. However, the counting is a little bit complicated because the photon counts for 2 states. If you remember our discussion of light, we said it could circle to the right or circle to the left. That's actually 2 ways that it can count. So we say that the photon has 2 degrees of freedom. This is also true for the gluons. They have 2 degrees of freedom. On the other hand, the force carriers for the intermediate vector bosons actually have 3 degrees of freedom. So when you add up all the ways that objects can spin and their antiparticles for the boson, you find 29 bosonic degrees of freedom in our universe. Well, 96 does not equal to 29. And therefore, our universe has no hope of being supersymmetric as we have seen in the laboratory thus far. So it looks like we don't live in a supersymmetrical universe. Well, there are reasons why we would want to live in such a place. One of these reasons has to do with energy. You would like to believe, and certainly we scientists believe, that there's a state of lowest energy. In physics, this state is called the vacuum. When you look at the concept of the vacuum, in the world of the quantum, it is not as simple as you might imagine. You might think the vacuum means there's nothing there. But in a quantum mechanical universe, particles can spontaneously come into existence if they come as a particle-antiparticle pair. That's what a quantum process is all about. And so rather than thinking about the vacuum as a state of nothingness, if you accept the principles of quantum mechanics, you have to think of it instead as more like a writhing sea where particles are popping in and out of existence. And that's what you mean by the vacuum. It's something of a much more sophisticated structure. And so the question that becomes, how do you calculate the energy of the vacuum? Well, in fact, using the mathematics of quantum theory, this is a very difficult question, with one exception. It turns out that if the universe is truly supersymmetrical, then the vacuum can be shown to be a state of lowest energy. Absolutely a state of lowest energy. And that's what you really would want for a vacuum. A vacuum should be the state where you can't remove any more energy from the system. So there's a very practical reason for thinking that the universe might be supersymmetric. But on the other hand, I just gave you guys a count and we found the universe is not supersymmetric. So there's a dilemma here. How do we resolve this dilemma? Well, it has been now about 100 years or so that physicists have been thinking about the world in terms of fundamental particles. One of the things that has occurred is that when you see something funny in the laboratory, we have gotten used to the idea that maybe we can imagine something that's better. I earlier told you about the weak nuclear force as being that form of nuclear energy that turns a neutron into a proton. Well, back when this process was first discovered, our technology was such that we could measure the neutron, we could measure the proton, and we could measure the electron. But we couldn't measure the neutrinos. Now, that leads to a bit of a problem because if you actually watch this process, you would watch the neutron disappear, and then out would come flying one proton and one electron. You could measure the momentum of each because we could measure their velocity, we knew their masses. We could also measure the energy that they contain because motion contains a kind of energy known as kinetic energy. When you did this in the days of the original experiments, a great crisis arose because if you took the energy after the decay, it didn't add up to the energy before. This is also true for the momentum. So, if that were true, it means that energy and mass are not the same thing. But that's what Einstein's famous equation E equals mc squared was all about. The physicist named Pauli entered this debate and said the reason that we think that energy and momentum are not conserved is because something is escaping our detectors. This something we now know is the neutrino. So the moral of this story is if you want something to be true, we are allowed mathematically to imagine a slightly different universe, but then we must later come back and ask the question, is this different view of the universe something that can be supported by an experiment? So now, let me take you to a supersymmetric universe. In a supersymmetric universe, in addition to the ordinary up, down, charm, strange, top, and beautiful quarks, along with the electron, the muon, the tau particle, and their associated neutrinos, there must be other objects that are their mirror pairs, because symmetries ultimately are always about some kind of a balance. Now, we have a favorite movie for showing this. It's our ladder. We know that if we have our ladder laying flat, then we can draw two squares that represent the area, one where the ladder is the base, the other where the ladder is the top. And so the green ladder here has an area that's always the same as the area of the blue. But we can also take our ladder and put it precisely against the wall. in which case the area of the green then is equal to the area of the brown. So if you want to have a symmetry, you've got to have some kind of sense of balance. In our supersymmetrical universe, therefore, in addition to the ordinary matter and force carriers that we've seen, we have to allow for the appearance of a new set of objects that have never been seen in the laboratory. So, there's the graviton, which we know from Einstein's equation of general relativity. If the universe is supersymmetric, there's an object that also carries the gravitational force. It's the message carrier for the gravitational force, but it spins at the rate of 3/2. The rate of the graviton is the spin rate of 2. In our world, we have an electron. The electron spins at a rate of 1/2. In a more balanced world that's supersymmetric, there must be an object which we call this electron, which spins at rate 0. In our world, there are up and down quarks, each of which spin at a rate of 1/2. In this more balanced supersymmetrical world, there must be up and down squarks whose spin rate is 0. And so if you look at this final picture, you can see it is balanced, and that's what we mean by a symmetry. You can think of our latter example where once again we saw sort of mirror images of certain squares. So this is what a supersymmetrical universe would look like. For every piece of matter, or every particle of matter that we know, and every message carrying particle we know, there would be what we now call a superpartner. So the superpartner to the photon, which is the message carrier for electromagnetism, would be an object called the photino. The superpartner to the electron would be the selectron, and so forth. And the superparticle to the Higgs would be called the Higgsino. So now this is all mathematics, and this mathematics was invented in the late 60s and early 70s. But the thing that's interesting about this mathematics is we've never actually seen these objects. We've never seen the things that would, if they're there, stabilize the vacuum, for example. They would also have the role of making our universe a more balanced place. Now, energy, as I said, is a conserved quantity, and it should be conserved and have a vacuum. So what do we do about the absence of these particles? Well, there are two things. First of all, you can say that this supposition that the universe should be supersymmetrical is itself wrong. Now, let's go back and review the string, because we know that for the string, in order to banish the tachyon, we absolutely had to require supersymmetry. Now, remember, that's with regard to the strands. Remember, ultimately I have revealed that the string is not a single object. You should think of it really like a musical instrument. So supersymmetry at the level of the string essentially says that the number of strands of the bosonic variety should be equal to the number of strands of the fermionic variety. But the particles in our world are not the actual strands of the strings. The particles that we know are the objects that correspond to the notes that the strands produce. So it's conceivable that even though the strands are supersymmetrical, namely come in pairs, maybe it's the case that in our universe we do not actually see the notes in pairs. There are a few such models, few such mathematical constructs that have this property. And some of these constructs precisely come from strings. On the other hand, most of the constructions that one can get from string theory not only has the strands of the string coming in pairs, they also have the notes coming in pairs. So the vast majority of the community of physicists who study string theory also are committed to the idea that we ought to, in our world, things that should be accessible to us, ultimately be able to find these superpartners. But we haven't so far. Why not? Well, there are several possibilities. One is simply a matter of mass and a matter of energy. You see, in order to see these superpartners, we have to have the technology that's capable of producing them. We've never actually achieved that level of technology so far, and it also will depend on how massive these objects are. Now, why does that play a role? Well, if we make a guess about the mass of these missing objects, the typical numbers are someplace between 300 and 1,000 times heavier than ordinary matter. Now, the other thing that's interesting is how fast is our technology advancing? There's a way to estimate this, which is simply go back and look at the history of how we detect particles and plot their masses. There is a simple assumption that we can make about making such a plot, approximate this plot by a straight line, and you get something that looks remarkably like what's known as Moore's Law. I don't know if you've heard of Moore's Law, but roughly speaking, it says that power of computers doubles once every 2 or 3 years. And this has been true in the computer world for over 20 years, which is why computer technology continues to improve. We can apply this same kind of logic to our ability to detect more and more massive particles. If you look at the history, you find out that we progress at a rate of about 3 GeV, that is giga electron volts, which is a unit of energy, on a year's basis. Now, what that means is the following, that if superpartners are on the order of, say, 300 times as heavy as ordinary matter, then perhaps around the year 2016, someone in a laboratory will produce one of these objects. On the other hand, if these objects are 1,000 times as heavy as ordinary matter, then it will take something perhaps like 200, 300 years to actually produce them in the laboratory. So we have to count on nature being very kind to us to reveal the supersymmetric structure of the universe. Now, the other thing about this supersymmetric structure is that it will also depend on our rigorously supporting experimental physics. In our nation, about 10 years ago, the community of particle physicists wanted to build a device called the superconducting supercollider. Ultimately, it was decided that this device was too expensive to support on the scientific budget of our nation. And this device is not coming back. As I often tell friends, it had a stake driven through its heart, so we don't have to fear the superconducting supercollider, or the so-called SSC, coming back to cause disturbances with our nation's finances. On the other hand, the Europeans have invested in a machine which is, roughly speaking, about a third as powerful as the superconducting supercollider would have been. This device is called the Large Hadron Collider, which I've mentioned before in these lectures, and the acronym is LHC. The LHC is in construction right now in the year 2005, with a scheduled end date for construction to be 2007. At some point after that time, the machine will be commissioned, that is, turned on, and typically with such complicated technology, there must be a period of sort of a shakedown when you must verify that the machine is working as you designed it, so that's one period, and then you have to put detecting devices into the accelerator in order to look for these tiny particles. It is perhaps ironic that to look for the tiniest things, you actually have to spend more and more money. But that's, in fact, the case where we need more and more advanced technology to look at these smaller and smaller objects. Now, at this stage, our nation has made an investment. We have spent approximately $500 million to put detecting devices in the Large Hadron Collider. So in this way, we Americans will participate in the search for what lies beyond the Standard Model. Many physicists are convinced that supersymmetry is one of the things that will lie beyond the Standard Model, and that the LHC will be the place where supersymmetry is found. But it's not guaranteed. In the year of 1980, I was visiting the campus of Berkeley in California. And there I encountered one of the physicists that introduced the idea of supersymmetry in the Western literature. When supersymmetry began, the Cold War was still underway. And so this topic actually has a bifurcated history where it was discovered independently by Russian physicists and by Western physicists. The Western physicists who made this discovery were people by the name of Bruno Zumino and Julius Vess. In 1980, I was visiting California and I made a stop in Berkeley. Professor Zumino was a faculty member there. Why did I pick the year 1980? Well, 1980 was the first year that this mathematical idea of supersymmetry was applied to the Standard Model. Prior to that point, theoretical physicists had been studying this mathematics, but they had not applied it to the Standard Model. There were some papers written that year by two independent groups, one of them at Northeastern University. They were led by physicists whose last names are Arnowitz, Champs-Sedin, and Nath. And then there was a separate paper written by a group of physicists in Europe. And the second group included the Italian physicist Ferrara, who again was one of the discoverers of the mathematics of supersymmetry. And these papers were the first time that people said, let's try to embed the Standard Model in a supersymmetric context. These papers were the first times that suggested that mirror set of particles that we saw on the transparencies. So there was a lot of excitement in the physics community. And on encountering Professor Zumino, I said to him, gee, isn't this a great development? The mathematics that a number of us had been involved in for a number of years was suddenly looking as though it's going to become physics. And to my very great surprise, this man who is one of the fathers of this idea looked at me and said, maybe. Sometimes ideas in physics turn out to be correct, but not in the way that we think they are. In the Standard Model, we have talked many times about the gluons, the intermediate vector bosons. There's a very special set of equations to describe these things. They're called the Yang-Mills equations, named after the two physicists who invented these equations in 1954. However, when they invented these equations, they were actually trying to understand forms of matter that are related to protons and neutrons. It turns out that these equations applied to protons and neutrons are miserable failures. And yet, the mathematics that comes out of this attempt is so potent and itself so intrinsically correct that some 20 years later, it was used to describe the weak intermediate vector bosons. In a series of papers that physicists such as Glashow, Weinberg, and Salam wrote. About 10 years after these theoretical papers were written using this mathematics, these objects were found in the laboratory. So even though the initial attempt to apply this mathematics was wrong, the mathematics ultimately came back and described something that we've seen in the world. It is completely possible that supersymmetry might follow this route. And this is why Professor Zumino had some skepticism. Even though many people who have studied supersymmetry find its mathematics exceedingly elegant and exceedingly convincing, until we see it in the laboratory, we will not know if this mathematics is a description of our world. It is possible that this mathematics is being applied in an incorrect way, precisely in the way that the Yang-Mills equations were applied when they were first invented. If that should be the case, I'm confident at some point in the future, 30 years, 100 years, these equations will come back and be found to describe something else in nature of very great importance.